Okay, so continue on a little bit about the data clipping, and we were talking about how that relates to bit depth and dynamic range. So if you manipulate the image outside of the bit depth or beyond the dynamic range, data clipping occurs. So again, if you increase the window level, you can make your image too dark to visualize the anatomy, or if you increase the window width, it will decrease the contrast beyond the limit. So basically the rule here is don't mess with the image too much once it's up. You can manipulate it a little bit, but remember you have to send it to a radiologist, and you could actually be losing information by manipulating too much. So what is bit depth again? And this is just a brief review. Bit depth is the maximum range of pixel values that the computer, the monitor, or any device can store, but it doesn't include software, okay? So simply put, it's just the number of grays that are stored in the system. And remember, we have a bit depth of 5, or a range of 32. So our range is really narrow compared to what the system can manipulate. And so remember, the more bits you have, the more grays you have. So dynamic range compression is basically playing off that, well, if you're a human and you can only see 32 levels of gray, then why are we showing you everything or showing you such a large amount? Because you can't see it anyway. So bit depth is the range of gray levels that the LCD monitor, the hardware, has, and dynamic range is the range of gray levels over the whole system, hardware and software. So dynamic range and bit depth exceed the range, obviously, for human vision. So this dynamic range compression helps save the computer storage space. So it's just a way to conserve on the memory. Another name for DRC is equalization, and we'll get into that in a second. So essentially what happens is in dynamic range compression is the really light areas of the image are darkened, and the really dark areas are lightened so that you have a more uniform image. It basically equals out the gray tones so that you actually have more gray. And I'll show you what I'm talking about. So if you look at this image, the image that's over here on the left, this is pretty black and white, okay? And you might be missing this pathology that's down here. This image is too dark with high contrast. So you can do a dynamic range compression or a tissue equalization, and it's going to take these dark areas that are in this image, the dark areas in the pixels, and it's going to lighten them, and it's going to take these light pixel areas and darken them, and as you can see, now on this side, you have a grayer image. So it equalizes the tissue contrast with more gray so that you can see the pathology. In old film screen or conventional X-ray, we used to have to do soft tissue images. So this is, if you're looking at this right here, that soft tissue, you are not going to be able to see the lesion or the edema that's underneath the patella unless you do a soft tissue, and you've lost bone detail here. But as you notice in digital imaging, you don't need to, because you can window and level, but it does a great job at capturing both soft tissue and bone detail, so it actually does a great job equalizing with tissue equalization anyway. So what is detail processing? You know what detail processing is because you've used it before. Edge enhancement and smoothing are two examples of detail processing, because it's either sharpening the image or softening the image, okay? So again, detail processing is going to allow you to process fine detail separate from the density and the contrast. So again, this is just like what we were talking about in George's class. Brightness and contrast are really manipulated by the KVP and the mass. Detail is something different. So on the system, it's the same thing. They call it decoupling local contrast from global contrast. And essentially what that means is you can manipulate a specific section or object on the image without changing the entire image. And again, detail processing can be manipulated or executed in either the spatial domain, which is the matrix, or frequency domain. It's not going to be manipulated or executed under intensity domain, because intensity domain is what's changing the brightness and contrast, and detail processing is not doing that. So we're going to talk a little bit about the kernels It's a processing operation, but what it does is it's a sub-matrix that allows you to do some very specific processing, specifically edge enhancement and smoothing. Okay, so edge enhancement uses kernel processing to sharpen the image. You do not want to overdo this or you're going to lose the fine detail, and you'll see this in a second. Larger kernels have more pixels, so you want to make sure this, you don't choose this, but the system will need to have larger kernels. If the kernel is too small, then you're going to lose the detail, okay, because it's going to be smaller than the detail that you're trying to apply. This is a great example of edge enhancement that's maybe using a kernel processing operation. So you can see the conventional processing on the left. It's great detail, okay, you can see everything. This is a great image, but you can see that this image on the right has a little bit more detail, okay, it's sharper. But it also has a little bit of noise. It looks a little grainier than the one on the left. So the one on the right is going to be sharpened, but a little bit grainy. Okay, an unsharp mask filtering. I'm going to briefly discover this. It's a 3-step process to do image subtraction. I'm not going to spend a lot of time on this because basically that's a special procedures thing, and we'll cover it later. Really what I want you to know are the 3 steps. Step 1 is going to create the unsharp mask. Step 2 is going to be the positive image, which basically is going to flip it from black to white. And then step 3 is the subtraction of the positive mask. Okay, so if you look at this next image, this is kind of giving you an idea of what's happening. So you have the original raw data on the left, the unsharp mask, which is a little bit grainy here, and then extreme contrast application here. So it's supposed to give you a crisper image, and it's going to mask out some of this background so that you really focus on just the bone detail. Okay, again, that's just an example of how it would look for a hand. It's mostly used in angiography, special procedures, cardiac cath. Smoothing, using a kernel processing, is the opposite effect of edge enhancement. It doesn't sharpen the image, it actually softens it to minimize the noise. So in edge enhancement, you may have sharper edges, but you're going to have more noise. In smoothing, you're not going to have sharp edges, but you're going to lose the noise. It's going to decrease all the noise. And there's 2 different types of noise that you can see in this system. So under the spatial domain, the kernel operation is best for random noise, which is quantum model. The best way to rid the system of quantum model is give it a little bit more mass. The frequency domain is best for electronic or periodic noise. So that's going to happen throughout the system. And the frequency domain operation system, these are software systems, are actually going to fix that. So here's a good example of smoothing, okay? So smoothing, you can see the image on the left is very grainy, and so they've applied a smoothing processing. It's still not crisp. It almost looks a little blurry on the right, but you have lost that intense graininess. And that is it.